Okay, anyway, so my idea today is to speak a little bit about entropy. Okay, so not just do the standard definition of entropy, which probably I will not write down, but try to give some geometric picture of what entropy means, especially the interpretation which is more suitable for what we want to do. Okay, so okay, so let me try just to do it with a picture, okay, and then we see how this picture arises naturally in the type of dynamics we always care in this business. So this segment here is meant to be a piece of unstable manifold. Okay. Now, when you iterate this piece of unstable, it's supposed to grow. Now, when it grows, if you are like times 2, for instance, where the interval is the full unstable, you go through different fundamental domains. And so this generates some cutting here. And so when you bring these guys, you have each of these guys is magnified into the corresponding guy. Okay, then what you are trying to measure here, and that's what entropy is trying to measure, is a measure of information you get from this process. So it's how much information I gain after one iterate. And that is typically entropy, which tells you that, which is you look at the probability of this times the log of probability of this plus the probability of this times the log of probability of this, blah, blah, blah. And this function, sum of pi log of pi, is the information function essentially, which is nothing but the integral of log pi, where you are integrating over each atom so that you get pi. So actually it will be like this, where px is the atom you are, and then since this is a finite partition, this value is constant on the atom where you have pi, and that's why you get this business. Okay, so this sort of cost functions or information function is this guy. And it's in a sense telling you how much knowledge you are gaining or not gaining, by the way. So the main properties of this information function tells you that if one of these atoms have full measure, then you are not gaining any information. So 0, because, well, I'm sorry, you're gaining full information. That's why you get a 0. So there is no uncertainty. You go directly here. And in the worst situation is when all have the same probability, in which case you have no information at all, no clue at all, in which case you get log 4 in this situation. Okay, now what are these probabilities pi that I'm talking about here? Well, you have your background measure mu. You condition along these unstables over a point x, and that's what it is. Okay, so this would be the full So if I consider the full unstable, then this, as always, is a Radon measure. So it's not a probability measure. So I want to restrict my attention to some atom here. So let's say I have a partition psi u of x. And then I just restrict my attention to this partition. So instead of doing that, I can just restrict there, which is the same as taking these conditional measures, which now are probabilities. And then I compute it on these guys. Let me see if I'm doing it correctly. Yes, correctly. So if the point x is here, then I bring back the corresponding atom. So it will be that. So I look at this conditional measure. This is the pi. I take minus log, and I integrate. And I just integrate d mu. So I could do it in two steps. First integrate with respect to all the points inside the same atom, and then integrate over all atoms. But instead of doing that, I just integrate d mu and do the two steps in one thing. And actually, this can be done as soon as I have some partition psi, even though this partition may not be, so may have empty interior inside the unstable manifolds, I can still define it as well as I have this partition. So, and that's my definition of entropy. So this is entropy of F given psi. And actually, the only thing that I really need to make this definition meaningful, I only need given psi, a measurable partition, so like in Rokhlin, Rokhlin 1, and assume F star psi is coarser than psi, which means, oops, sorry, now is better, I think, which means exactly what the picture told us. So it means that f of psi of x contains psi of f of x for mu almost every x. So that's the only two things I need, because once I have this, this is perfectly meaningful. If not, it also would be meaningful, but then it will not satisfy the basic properties you want it to satisfy. And then that's the entropy. So that's entropy of F mu with respect to psi. So that's a nice definition of entropy. The fact that it will at all coincide with the standard definition of entropy requires a huge amount of theorems and understanding what is the correct partition psi or family of partitions psi to one you want to analyze. This as well has to do, or is in a sense related a little bit with what we discussed in this Margulis normal subgroup theorem. When I define the set Q, the group Q, and I told you that is where I can guarantee that the measure is equivalent to Lebesgue. So it's where the measure is hard, which is exactly the place where I have invariance. And then there could be some dust outside that I have to make it disappear and make sure that this conditional measure is exactly Q. In this sense, this approach was a little bit different than what typically Margulis or Zimmer do, which is that they look at what is the largest group where you have something not trivial. And that would be the Q. Okay, so even if there are dust over there, you just put it everything in the Q. And then you show that whatever is inside Q has to be hard. Okay, so one is getting from inside, the other is approaching from outside. Now, why I'm saying that, I'm showing this picture, because the typical definition of entropy, which is not what I'm writing here, is you take P, a finite partition, you take this entropy, where now being a finite partition is the standard sum of pi log pi, and and then you take limit 1 over n limit. Okay, and it turns out that this is the same with this pretty much definition as hf from 0 to infinity of f and p, and since I'm going from 0 to infinity, this becomes naturally increasing. Okay, and now taking, and this is what is called h of fp with the standard definition. Measures new. Oops, this isn't equal. And then you take the supremum over all partitions. And taking the supremum over all partition, in a sense, is trying to approach from outside the unstable. Okay, so that's the purpose of taking the supremum over all partitions. The fact that you actually are approaching the unstable is never true. It's true at the entropy level. It's never true at the topological level, so to speak. The fact that this, even if you reduce the P, that this intersection, these atoms here, which, so the elements here are the intersection of okay, and I guess if I want unstables, I think I want the other way around, but it really doesn't matter. But forget, you go for the future and for the past is the same. So you don't care. So these are the atoms, and this, if you assume that P is like a ball of reduced epsilon, this is asking you that the points stay epsilon together all the time in the past, and that's an unstable manifold. Okay, but that's only true if you are like Anosov or very nicely hyperbolic. If you are not Anosov or anything like that, why this staying only by epsilon small is really giving you the unstable manifold. That's not true, and actually the fact that you have this definition being the same as the corresponding definition here by taking the correct partition psi is very hard. And what's the correct partition? I will tell you soon. But you can go and take even smaller partitions. Actually, I always have problem with what is smaller and larger with partition, because the atom of the partition, when I said smaller, I was thinking of atoms of the partition being smaller and even smaller dimensional, like interval versus two-dimensional. But the partition is larger because there are more atoms. Because the smaller the atoms, the larger the amount of atoms. And well, if you really understand this action, you are supposed to say smaller when there are less atoms, not when there are more atoms. But I have my geometric guy going in between. Anyway. So when I take psi, whose atom is smaller than the full unstable, or is not open, let's say it's one dimension less than the full unstable, then the entropy here will typically be smaller than the full entropy. Okay, but that's that's approaching from inside the unstable instead of from the outside of the unstable. Okay.
And so when the unstable is one-dimensional, when you say it's one-dimensionless, do you mean?
No, it could be even, so because it could be some fractal guys inside. So yeah, there is still room to be zero Lebesgue measure So the atoms of the partition here to be zero Lebesgue measure. There is still a possibility here.
But I think before you also made this remark that if you, in our case, zero dimensions in whatever meaning it would allow implies delta.
Yes, zero Hausdorff dimension. Okay. But it could be a Cantor set of positive Hausdorff dimension, and then things get fishy. But the problem, yeah, so that's part of the problem, and is a matter of being able to play it correctly. So how good are all these partitions we are talking about? So a finite partition, and that's why this is the favorite choice in most situations, because a finite partition is a beautiful thing. So this is a finite partition. Okay, so you have squares. The boundary may be bad, but still it's an open set. Okay, and that's beautiful. And then you choose it so that the boundary has zero measure, then it's even perfect. And if you are with Lebesgue measure, what else could it be better than that? Now, still a finite partition doesn't need to be that nice. It could be really much uglier. But we are working in metric spaces with manifolds. So if you have a finite partition, a typical atom, so you may have atoms which are just dust, but you should have atoms which has non-empty interior, or whose closure has non-empty interior. That's just bare category that tells you you need to have something. So these are not so far from here. Even though the first thing you need to be convinced in this game is that the mere fact that the guy has positive measure, or that the fact that the guy has non-empty interior is not much of a difference. Okay? Even though positive measure is just a dust Cantor set of positive measure, is as good as an open set. Because this is measure theory, this is ergodic theory, so really you capture all you need from there. Now, when it comes to these sort of partitions, this is a measurable partition, but it's not finite, so it's really uncountably many atoms which are doing whatever they want. So it's really very hard to catch them. So that's why it's so good to have some good partitions helping you. And these are these special partitions I was drawing. And let me put the first lemma, which is actually a theorem, but the paper I think is a lemma, which is Sinai. And this Sinai's partition. Okay, so what does it tell you? It tells you that whenever you have an unstable manifold, you have a nice partition psi u subordinated to the unstable manifold. So it says the following: let f from M to M preserve mu. F needs to be C1 plus Halder. Assume mu ergodic, and with at least, actually this is sort of redundant, but I will still do it, at least one positive Lyapunov exponent. Okay, Sinai prove it in the nicest situation of an Anosov system. Then you use Pesin theory plus Sinai's construction, and Ledrappier and Strelcyn make this construction into this general situation. Okay, so here actually is plus Pesin plus Ledrappier. Then, just to complete the picture, Wx is the y such that the limit as n goes to minus infinity of 1 over n distance fk fnx to fny log distance is negative. So that's how you define the unstable manifold. This is a manifold. So that's Pesin of a fixed dimension, which is the amount of positive exponent. And there exists a measurable partition psi u such that 1 psi u of x has bounded diameter in WUX and contains and is a neighborhood of x. In W of x. Second, when you iterate in the right direction, it gives you just a point, and the right direction should be the direction where it shrinks, so it should be negative n, I guess. So you shrink to a point. And 3, there is this operation, which this operation is better defined when you look at the sigma algebra instead of the partition. So let me write it. This is the intersection of sigma algebras. B of f so you take the sigma algebra generated by this partition, okay? And then you take the intersection over all of n. And this is the partition into the unstable manifolds. So this is the Borel sigma algebra mod 0, of course. So this means that if you have a set which is saturated by the atoms of Fn xiu for every n positive, then is saturated by this unstable manifold. Okay, for almost every point. So if you are always containing all these long unstable pieces, then you contain the whole unstable piece. So that's what Sinai is constructing, and all are important statements, but the most important is this fact of being a neighborhood of x. Okay, so that the guy is essentially a ball around x. And then once you know that, the main theorem after you have this yeah, let me just maybe one comment. Why I said this is superfluous, one positive exponent, because if all exponents are smaller than or equal to 0, then this is just a point. And then this is perfectly fine if you just take psi u of x to be delta, the point x, because then this is open and bounded in the unstable of x, and all the rest is completely trivial. So, but since it is so trivial when you just get no exponents, then it's better to get. So this theorem is Ledrappier-Young, which says that for this Sinai partition, this is the same as this. And after you know this, the consequence is that this, yeah, I mentioned it, so I'm allowed to do it. It tells you that this guy is the Pinsker sigma-algebra. So
finite partition.
It's a measurable partition.
Okay.
Somewhere. No, it's not finite actually. So, okay, good point. So, as a partition is partition which is inside these leaves. So, and you have uncountably many such leaves. So it cannot be a finite partition because it has to be subordinated to the unstable. So maybe I should have put it here more explicitly. This is inside these guys. Yeah, I should have written that. So each atom is inside the unstable manifolds of X. Okay?
It's a partition of M.
It's a partition of M, which each atom is inside the unstable partition, which is a neighborhood of X inside there, and is bounded inside here. So this is a copy of Ru, and this is a bounded set in these copies. Compact closure, that's the meaning of bounded here. Nothing else. Now, still there is a question of the fact that what happens in our previous picture. So I take one of these atoms, I iterate it by F, it gets longer, naturally. And then how many atoms lie inside there? Because this increasing property, did I say it's increasing? I didn't say it's increasing, that's even the, oh boy, 1/2. Okay, and this is this direction. Okay, it's an increasing partition. Okay, now how many of these guys appear here? It could be countably many. So it cannot be more than countable because each one is a neighborhood, so that doesn't fit so many. But it could be countably many without any problem. So then you bring these guys back and you have countably many of these guys. Still, these integrals are good, so it's not a problem. So why these quantities are finite numbers? Who knows? So there are a lot of theorems telling you that. And eventually, at some point in all these proofs, you are proving in between that this is a finite number in particular, which is equal to this other guy.
Indeed, if you have no exponent at least one, then all these psi u x's are going to turn into x.
Yeah, exactly.
And your entropy is going to become 0.
Exactly. And everything is perfectly fine. Yes. And that's yet one proof which follows from Ruel inequality, but here you don't even need it, even though you are using C1 plus Hildebrand. That shows that if you have all exponents less than or equal to 0, then your entropy is 0. Okay. So in this sense, it's a very, so it may not be a finite partition, but when you restrict to the unstable, in a sense, it's a countable partition. Okay, so that's what is important. And actually, not only in this dynamical sense, when you restrict to the unstable, it has to be countable, even though it's the full unstable, because again, every point is a neighborhood Every atom is a neighborhood of the point, so they are not more than countable. Now let me draw the picture of the proof because it's beautiful proof. I learned it, I have to say I learned the proof even before I learned the theorem, because I was trying to do something similar in one of my works with Arroyo where I was PhD at IMPA, and we came up with the same idea. And it's extremely natural, and I think it is beautiful. So I will give you first the picture of the proof by Sinai, and then I will give you even a different proof in the Anosov situation, because it's worth looking at what you should do actually in the Anosov situation. Even though Sinai did it in the Anosov situation, but he had less amount of information than Bowen, in a sense. Okay, let me show you the proof of Sinai. You take a point, any point, typical point, nice point. Okay, then this nice point will have a neighborhood and a set of positive measures around this point, where you have local unstable manifolds all being nice. So that's Pesin theory. Or in the Anosov situation, is even a whole neighborhood, local product structure is a beautiful picture. Okay, you fix this set, okay, and you are trying to define your partition, so you just define as these pieces of unstables on this place. So for x in A, you take this local unstable manifold of x, meaning this piece here. Maybe to make it more explicit, it's just this piece that is inside A. And that is supposed to be your psi u. Okay, so this will fail, but you will fix it. Okay, so you take these guys. Now what you do? You take any point y here outside. Ergodicity, because we assume the measure mu is ergodic, tells you that there is an iterate that will get inside here. Okay? Then once I take inside there, I take the first time, I take this atom here and I bring it back to this point. Now, what is the problem? The problem is so this automatically makes it the bounded diameter and be in a neighborhood, make it for free, that is inside unstable, make it for free. This, it just follows because you, after finitely many iterations, you get here, and then from here to 0, you go directly. This part is also almost immediate. The really thing that you lack is the increasing property. And what do you need for the increasing property? Well, you need that you can measure first here. When this point here comes back to A, you want this atom to really go all the way over. Okay, so what you want really to make sure it's not happening is that you come back like this. So of course this guy grows, so this guy is actually very, very long. So it goes here, it probably went again here and again here and do something. But one end went and just cut there. I didn't cross all the way. Then what is the solution to this? There is one correct solution and one wrong solution. So let me tell you what is the wrong solution. But at least would be the first thing I attempted to do at the time when I had to do it. You just cut. And then you cut. Because then this guy didn't came since I cut there. Okay? And then you keep on arguing. Now this is not, So if you try to make it work, you eventually land into a fact that you are cutting too much, and that's not good. So it's really a pain. So you have to be inclusive, all inclusive. So you grow. You go longer to make sure that you cross here. Okay? So you just add some amount, and this will make sure you cross. Now, of course, you have to be careful as well, because I added some amount. Now everyone is essentially a bit longer. And then this guy, I need to add a little bit more because I'm trying to reach, and it's just whenever I make it more, I have to go more, and so on. But this is an exponentially convergent series, okay, geometric series, because whatever I'm adding here, it comes from an iterate lambda to the n, okay? So it's just a summable guy. So this is not much of a problem. And that's the argument. You just increase until when you take the limit of all these increments, you get your partition. The diameter stays bounded because you only were increasing some small amount. You could start with a very tiny piece here, just knowing that you will have to increase. You start with a very tiny piece here anyway, and that's it. That's the construction, and it works. Just do the computation, and it works. So you make sure that your guy is increasing.
So how do you know that in the local, how do you know in the local unstable manifold that this, so you have enough height that you can keep increasing and eventually it will work?
Because you start with this local, okay? Now, you do your a priori computation. It gives you some sum of exponentials times some epsilon naught, okay? And the exponentials is the expansion rate, minimal expansion rate, that will appear there. Okay, now once you have all these numbers, you go here and start over with this set A. And then whatever expansion you are doing will belong to your other A. And you know how much you will be grow in the worst scenario. So then you don't have this problem. So that's how you control the guy. Okay, now let me tell you how you do it actually in the Anosov situation. Of course, there you have a huge amount of knowledge. So in the Anosov situation, you have a Markov partition. See, by these rectangles, where this is, say, unstable direction, and the other is the stable direction. Then that's your Sinai partition. You just take these segments. And the Markov property of the Markov partition is exactly this fact of being increasing. And that's, you don't need to do anything else. Okay.
Also, could you say what breaks if you just assume f is C1?
This guy is not a manifold. That this is, and there is an example by Charles Pugh, where he shows build a C1 diffeo with some invariant measure with non-zero exponent, whose this guy is not a manifold. And then the very starting point really makes a problem. And when it comes to this argument, you want the manifold and some control on the geometry of the manifold on this set of positive measures. Okay, so what you really need, you don't care about the function being C1 or not. You just want this to have these manifolds, these local unstable manifolds, and this property. Essentially, well, I draw it when you go forward. You can draw it. It's the very same computation, making it coming backwards. And you want this contracting property. Okay? And again, if the guy comes backward and it goes like that, you just add the little bit you needed to add. Okay, but that's what you need. You need to have these sets, even if they were not manifolds, this says we have some nice geometry where you can make this computation, these comparisons, and these drawings. So you need this. And once you have it, nothing else matters. Okay, now it worth mentioning as well, when you have no zero exponents, then you can show that, and that's actually, there is a very important lemma by Manier to this respect, which is useful for several situations. It's also useful for what I want to describe here, which says that if you take a function r from m to 0 infinity, actually 0, 1 will do, because you are thinking r being small here, not large. So let me even do it like that. You don't want it to be 0. You will see why we don't want it to be 0. And the integral okay, so you want some finite integral for this r of x. So that's why you don't want it to be 0. Then there exists a countable partition P. So it's not finite, but it's countable, such that the atom of P of x is always inside the ball centered in x and radius r of x for every x, or almost every x, rather, every x. Okay, so you really stay into these nice guys.
With the same hypothesis, or
This is a completely abstract. There is no even dynamics here.
yeah.
So it's a purely geometric statement in a sense. But now we apply it with the same hypothesis. There are maybe a little bit more of hypothesis. We apply it under the hypothesis that there are no zero exponents. And then we, by some suitable choice of R, then we pick this P and we do this guy here. And then we take, what is this guy? And this will be all the y such that fny is in the atom of fnx, and this implies that distance of fny to fnx is smaller than r of fnx for every n smaller than 0. And then Pesin theory tells you that if there are no zero exponent, this is inside the unstable manifold of x. And then I'm approaching, not by a finite, but by a countable, but in the previous argument, in the definition of entropy, the standard definition being countable partition is not really a problem. Oh, I forgot, because it's very important. The entropy of the partition is finite, because if not, everything will be a problem. Actually, there is a somewhat explicit bound with respect to this quantity here. And so in this way, you work a little bit more with the proof of Sinai partition and everything, and you see that you can make this partition subordinated to this Huyi partition. And that's essentially the proof of this Ledrappier-Young statement in the case that you have no zero exponents. Okay, and that's actually a theorem by Ledrappier, which was before the theorem by Ledrappier-Young. So when you have zero exponents, it's really much, much harder. And the reason why it's much, much harder is because you don't have this property here. So you still have this property, you don't have this property. Okay, the fact that there are some zero exponents tells you that in this guy, you will have some points in the zero exponent direction. So there are no points in the stable manifold, but you may have points in the zero direction. And that's
even if you have just one zero exponent?
Even if you have just one zero exponent, there are several situations where you can do it. For instance, if you really know that in the zero direction, so in the zero exponent direction correspond to an isometric direction, then you can do it explicitly. But even if it were partially hyperbolic with zero exponent can correspond to the center foliation, there may be a way. I'm not sure, but I think it's not at all easy to, and I'm not even sure if it is possible to find a function r of x which will be integrable and give you what you want. So maybe it can be done, but it will not be at all straightforward. When you are isometric, then it's not a problem. You just need the infimum of this function r of x to be 0 to make sure that in the, which you can do. So it's not hard to keep this property assuming the infimum is 0. Then you will have that you are removing all the zero exponent part because you are isometric. So whenever you reduce, you chop a good amount of your manifold. But if you are not isometric, then it really becomes much harder. And actually, they have, so the work of Ledrappier-Young is really quite hard piece of work to essentially to fill the gap from this definition to the other definition. So you have to show these two guys are the same, and you really need to work on. Okay, so that's crash course in entropy. And Pesin theory and Sinai partitions and everything. So let me tell you what else Ledrappier-Young is telling us, because they have paper 1, paper 2, and in paper 2 they give the formula. This is sum of delta I chi I. Okay, and hence, since this is XIU, the same is true for F. Now, if one starts going through the proof, you see that you can do it a little bit more axiomatically. You can put whatever psi you want, and then you will only look at the exponents corresponding to this partition psi, and blah, 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 which I will discuss later. One thing I should have said before is it follows from the theorem, but actually in the middle of the proof you prove it, that this quantity actually only depends on the unstable partition and not on this particular psi you built by Sinai you are choosing. Okay, which is not so, should not be so surprising because of condition 1, especially because condition 1 will tell you that if you take two partitions, psi 1 1, psi 1 2, psi u 2, you take, say, n negative, you contract one, and essentially you will make these atoms much smaller than that. This, of course, there are some known uniformities. This will happen on a set of 1 minus epsilon n measure. As you increase the n, you really are getting almost everywhere. And then you just put this into a proof to claim that the entropy using this partition, the entropy using this partition is the same thing. Well, actually, this gives you an inequality, but you can reverse the role of both guys, and this gives you the equality. Yeah, I didn't mention, but this entropy function has all the standard inequalities, essentially. When you increase the partition, then you get more entropy or less entropy, depending on what does it mean to increase the partition. But Anyway, so you have monotonicity of entropy and blah, blah, blah. Okay, so now I want to explain what are the quantities here. So what is this formula, which is a very important formula. So this is Ledrappier-Young entropy formula. So this is part of Fosseledets. It tells you that you split Tm at E1, En, you have exponent psi I, the measure mu is always ergodic here, you have the exponent psi i's, and you also have, and that's Pesin, now, manifolds, let's order them so that B1 is larger than psi2, larger than psi u, positive. This could be some psi as well, and then you have the negatives. Okay, then you have a manifold B1 inside B2 for almost every point x, B u of x, which is the unstable manifold of x. Okay, where each of these bi of x is E1 up to EI. Okay, so you have this flag once again. And the fact that you have a flag and that here we are playing with flags, and the fact that we are playing with flags also in SLNR is not coincidence, so it's part of the same game. It probably will become clear when we give a proof of Fosseledets theorem, the proof by Zimmer essentially of Fosseledets theorem. So you have these BIs, and then you can just consider this BI intersected with this Sinai partition and call it psi I of x. And this gives you a partition. Because this VI form a partition, this gives you as well a partition. The VI has a very good description as well. So VI of x can be classified as 1 over n log distance fn x to fn y is extremely smaller than psi I plus 1 limit. And you go to minus infinity. And if I'm doing this, and n is negative, so yeah. But this is a positive number, so yeah, now it's good. I think now I'm right, yes. So these guys are characterized by the speed of conversions to the business. And notice that when I is u, I'm getting psi u plus 1, and psi u plus 1 is the 0 appearing here, essentially. Okay. So now once I have this psi I of x, we can look at these measures, which again, for the geometric quantity, you can go and define, like we did with this Rokhlin second theorem, these guys, and this is just the restriction of this guy to this atom normalized. So this thanks to this open property of the atoms. Anyway, so you show that's a very important theorem, actually, non-trivial, but still, I will show how the proof goes of all these theorems in a very simple situation later. that this number, oops, this number of log of mu epsilon going to 0 be that these numbers exist and is independent of x. And this is actually what is called the dimension of this measure. So this is actually the upper, lower, or lower dimensions. You take lim sup of lim inf to make sure this exists, then it's upper or lower dimension. And in this dynamical context, Ledrappier-Young showed that this number exists and is independent of the point x, thanks to ergodicity, plus a lot of things, but in particular ergodicity. So this is di. And what is delta I? Delta I is di minus di minus 1. Okay, so what is the picture of this? Let's assume the easy case, u equals to 2. So we have two different exponents. We have a faster direction, which is the v1. The v2 now is the whole unstable. Then the d1 is equal to the delta 1 naturally. So I didn't say, but you can. So the first guy is the 1, or you can put the d0 equal to 0 either way, which is actually that. You take the conditional measure and you look at the dimension of the conditional measure. Now, when you look at the delta 2, you would like to claim that it is the conditional measure along this direction, which is slower, and then take the conditionals there. Now, the first problem you face is that this lower direction doesn't even exist, so there is no foliation. Because you have the flag, you don't have this transverse foliation. Even if it exists in some sense, it's not true that when you take the conditionals along this other foliation, the conditional will have the corresponding dimension. Then what you do is this delta 2 will be some sort of transverse dimension. What does it mean? I take the total measure, I look at the dimension of the total measure, I subtract the dimension of this guy, and I should get in this. And this is exactly the same as doing the following different construction, and that's how the proof goes actually. You take the quotient measure, which is just a measure on a transversal here, which is just the measure of the segment here. You saturate a little bit, and that's what it is. And then you look at the measure of this transversal and at the dimension of this transversal. Now, to be able to compute the dimension and make sense the dimension of this transversal, you need that this fast foliation be at least Lipschitz. Because you are computing balls, and you want to make sure that this transversal and that transversal, or that transversal, is the same. And to make sure that this transversal and this transversal is the same, you need that this holonomy be at least Lipschitz. So that this b epsilon is the same measured here or measured there. But, well, that's true. This foliation is Lipschitz. So this is not a problem. And then this quantity is so this transverse quantity is independent of the transversal. And if you want, you could define delta 2 as being this transverse guy. And the theorem says that this actually coincides with this. That's, again, it's a very geometric theorem. It's quite general in geometry with the correct assumptions. So these are the delta i's. The chi I are the Lyapunov exponents, and this is the formula for the entropy. So each direction is contributing some amount. And now in this respect, I can even go here from I0. This is an increasing partition, so I can write down this entropy, and this will be the sum from I equals to 1 up to I0. And this is perfectly fine. And it's a very flexible proof. So let's say, for instance, you have a co-cycle type of system. So T from omega times M, where T of omega x is F omega G sub omega of x, or these G sub omegas are, say, C1 plus Hölder and blah, blah, blah. You have an invariant measure now for this product system. Now we can do the whole theory of Lyapunov exponents and blah, 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 just thinking on the second coordinates. Okay, and then Sinai will give me a partition, an increasing partition subordinated to the second coordinate. And even Pesin will give me all the VIs, so I will have the very same formula holding there, with the very same definition. So this is sum of this delta I psi I. So, and now this I naught, this psi I naught, is fully subordinated to this. So this is completely missing the entropy contribution from the base. So it's not talking anything about this entropy contribution. We are just looking inside there. Of course, this F, this omega part of the dynamics could be very smooth, an Anosov system, whatever, and then you will have the full entropy. Sure, but I don't care. I'm just trying to look to this other part. And the proof just gives you that. So you just run the proof, and essentially you get this. Okay. You don't get the first part of the theorem. You just get the form for this very special partition. So you cannot relate the full unstable in the fiber to the full entropy. Well, you can, but then you have to define, for instance, in this situation, you will have to define h of f given the fibers, essentially, so which is subordinated to the fibers. So you have to define this, which definition we pretty much put in a WU corresponding to the fiber. Anyway, but it's a very flexible guy. Now, time is almost up, but let me at least give you a very simple picture of the proof. I will do it in ×2, which is, in this case, a completely trivial proof. So this is not an invertible dynamics. You can think on the solenoid for that matter. Still, the picture will only require this game here. Now, what is Sinai partition here? Sinai partition here is essentially a trivial partition if you look at it from the circle point of view. It's just, I will write it the interval 0, 1. But if you think on the solenoid, what you are doing is you have all this solenoid going around the circle, and you just chop it here, and you get these circles, but on each guy. So that's what you're really doing. Then when I do f psi, or f minus 1 psi, whatever it means, so what I'm getting is this atom and this atom. And when I keep on iterating, I'm taking the dyadic partition over there. And then comes the first important theorem here, which is Shannon. And all the theorems here goes to the same thing. Shannon-McMillan-Breiman. So this is the first important theorem to know. As always in this entropy business, we tell you that the entropy of Fp is the limit as n goes to infinity of 1 over n log minus the measure of the partition Pn of x, where the partition Pn of x is the wedge from 0 to n of Fnp. Okay, so that's the first thing to know. The second thing to know, and again, all this theorems are very flexible, so you can use this definition of entropy, that definition of entropy, that definition of information, and most of the time you can make a version of this theorem that suits your necessity, in the sense that I could take here conditional measures, for instance, with respect to whatever other partitions and play some games there, and things will be good. And just to remind you the proof, this is an application, so the proof of this is the ergodic theorem plus properties of information functions. Now, something that we don't need here, but it's also important how to put this into context, and it's again an instance of Magnier theorem playing around, even though they don't use Magnier's theorem, but one could more or less use it. It tells you that same thing happens with what is called Bowen balls. And actually you have to take epsilon to 0 as well here. So where Bn epsilon of x is Bowen ball. So it's the y such that distance from kx to ky is less than epsilon from 0 to n. So this is an approximation of the Bowen ball, and the game is that this is pretty much Pnx. So these two sets are very much related, and once they are very much related, you show that this limit here is the same as this limit here, and this limit here is entropy. So that's morally the game. Now let me maybe just do one stupid comment, but it's fundamental and very important, even though I'm running out of time very badly. So if you take f minus n of this is p minus n on f n of x, or something like that. Okay? So as soon as this point is, so you have these conversions almost everywhere, and if you on top of it has conversions in measure, this tells you that going to the future or going to the past is exactly the same. And that's how you actually relate the unstable being the same as the stable. And it's this fact that the Pinsker for the future is the same as the Pinsker for the past, and the unstable then is the same as the stable. So this is all part of the same game. Okay, so, oh, I'm really bad. Okay, maybe let's draw from Wednesday. I finish the proof of this. So it's really one computation, but let's do on Wednesday. Okay, sorry. Thanks. Okay, let's start slowly with the picture we were doing last time. So I want to go over one picture before I concentrate on the proof of Ledrappier-Young, the model of the proof, so where all this business come from somehow. Of the Ledrappier-Young formula, actually, which is the importance of the Shannon-McMillan-Breiman. Is really something which is very natural, but it's still extremely important. So you already, well, I don't know why I'm drawing a square. I think the same thing happens in an interval or in any dimension. Okay, the point is, you want to cover with cubes of size 1 over n, or of size epsilon here. So how many cubes I need? And there are two ways of doing the computation, and both are very powerful. One way is I count and I cover and I count how many. That's one way, here and there and so on. The other is the measure of this guy is epsilon squared, the measure of the total is 1, is 1 divided by epsilon squared. Okay? So both are valid, both are very useful, and the fact that both give the same answer is magic, but it's what is about mathematics after all. Oh, and that's what Shannon-McMillan-Breiman is telling you, after all. Because it's Shannon-McMillan-Breiman is, I take this partition and is asking you what is the cost of covering this interval with this partition. The cost is the entropy. Okay, and then what is Shannon-McMillan-Breiman is telling you? Well, you just focalize on this guy, look at the measure of this guy, pretend this is the only guy, or all measure the same. That's the cost. So you're doing 1 over epsilon squared. Now here you are, instead of considering areas, you are considering entropy. Doesn't matter. So it's just the same philosophy. So, but this is a very powerful fact. The fact that I can just concentrate on one guy, on how fast this guy is shrinking, is already telling me how many guys I need to cover. So with this in mind, this is what we have in our formula. We take times 2. Is 2x mod 1. And we take this dyadic partition. So this guy and this guy. And we have that the n of x is this partition. Let me show you. Is a over 2 to the n, a over 2 to the n, probably n minus 1, really doesn't matter. Well, it depends on how I count. So if I put 0, no, it's plus 1. Because if I put n equal to 0, I want the 1/2 partition. So is this where x, the points in the boundary, doesn't really matter? Well, they may matter, but we can see that all the points in the boundary are pre-periodic, so no measure will be carried there, no invariant measure will be carried there. And is this where a is a of x, which is nothing but the integer part of 2nx or 2n plus 1x, I guess. Something like that. Okay, so these are the partitions. And once we see it, we are asked by Shannon-McMillan-Breiman what is the measure of this Pnx log of it divided by n. Okay, but this is nothing but 1 over n log of the measure of the ball centered in the middle of these guys, so some points xn that I will not discuss who is the point, and radius 2 to the minus n plus 1. And for that matter, will not change anything if I define, if I take the limit there with n plus 1, and then instead of taking this, I could take log 2 to the n plus 1, and let's keep the limb here, and multiply this by log 2, which is the expansion coefficient. And then if you remember what's the definition of dimension, this is the definition of dimension. So, of course, there is some subtlety which needs to be addressed, especially the fact that this is a point xn, which is moving then you should be a little more careful. And being more careful here is not really a harm. I take a point x, whatever point x you want, where Shannon-McMillan-Breiman is working, okay? And then I just can make some adjustment of this 2 to the n plus 1. And I actually should do 2 adjustments, plus or minus, one that goes outside and the other that goes from inside the guy. Well, it should be actually, well, the minus is negative, the plus is positive, okay? And then this guy is actually exactly the same as this. Well, it's in between these two balls, so I will have both inequalities here, but this shouldn't harm, because this business I can multiply and divide by log 1 plus. And since this epsilon n is going to 0, this really is not contributing to anything here. Even, well, one should show what I'm saying, but actually this guy is supposed to be with the n plus 1, and even this guy should be going to 1. But that again, that can be shown essentially from the picture, that you lie most of the time close enough to the middle so that this is good enough. And that's pretty much it, because once I can handle this, get rid of this, which I multiply and divide actually by this guy, then this is dimension. So this is now truly definition for dimension for almost every point x, which is for the guy. Now, I didn't knew that dimensions existed at points. I, as always, could be talking about upper dimension, lower dimension at every point, but I'm not doing that because I have Shannon-McMillan-Breiman telling me that this limit actually exists. Okay, so this implies that this limit here exists, which implies dimension at the point x exists. And its value is entropy divided by log 2. And that's the Ledrappier-Young entropy formula. Entropy for mu, 4 times 2, is dimension times the Abramov exponent, which is log 2 here because it's just times 2. Okay, so that's pretty much what it is. That's how the proof goes. Essentially, in all cases, when you have this nice conformality and you can actually claim that this guy is exactly the ball of radius 2 to the n. Okay, so in the case of, so this game here with the epsilon n I'm talking is actually part of this Brin-Katok, which they do it in much more generality, because if you do the bow and ball with here epsilon is essentially 1 or 1/2, something of the sort, this is actually the ball centered in x and radius 1/2 to the n plus 1. Again, doesn't matter. So that's exactly in this times 2 situation. Okay, and the fact that you can go from bow and balls to this partition is more or less what I was discussing here. So that's the reason why you have this amazing formula, which, as I said, is entropy supposed to be about coverings, but Shannon-McMillan-Breiman is telling me that entropy is also about infinitesimal geometry. The same thing as dimension. You have something which is called box dimension, and even Hausdorff dimension as well is about covering, how much you need to cover. But you have infinitesimal dimension for measures, for instance, which is this definition. And all these quantities are related. They are not always the same, so it depends really on regularity of sets. Sets are very bad, and then different definitions give you different numbers. Different definitions have different properties. But when a set is reasonably nice, all definitions are the same. The infinitesimal is the same as the global. And this is how things work. So it's not trivial to show, even though the definition suggests that something like this is reasonable to expect. So you can define the Hauser dimension of mu. Actually, this is not uniquely defined, so it depends on the author whether it defines one way or the other. But you can define it as the infimum or A of the Hauser dimension of A. Okay, so it's the smallest Hauser dimension among sets of positive measure.
So here mu is some measure absolutely continuous with respect to what?
No, here is mu is any invariant measure. So ergodic, I guess. You don't really need ergodic, but if it's not ergodic, then dimension will depend on the point. And the reason why dimension will depend on the point is because, again, even if the measure is not ergodic, Shannon-McMillan-Breiman tells you that this limit exists almost every point. And then dimension exists almost every point, so that's automatic. Now this is dynamics. This here is just geometric theory of measures. So it's any measure in any metric space. Hauser dimension is defined in any metric space. And there is other sort of dimensions where you can ask this set of B of full measure instead of just positive measure, or you can take limit asking the measures to be larger than 1 minus epsilon, take limit with epsilon positive. And typically, most definitions do not coincide, but they do coincide in reasonable situations. And then, as I said, so the standard definition, upper, lower, so is the measure mu at a point x, because it's something that depends on the point x, is limit as r goes to 0, no need for the minus, divided by log r, which is actually telling us that this guy is likely r to the d, and you have the upper and the lower, of course, and then you can do bounds of Hauser dimension, which you are supposed to cover by sets of diameter r, and you take power d, and this power is what determines what is this Hauser dimension. Then you can bound this number in terms of these dimensions. Again, upper and lower give different bounds. And once you know that the dimension exists at every point and is the very same number, then, which is our case, then you really can essentially show that this Hauser dimension here is the same as this delta mu that is appearing here. So these two definitions will coincide. And even, again, by the very relation of entropy and this Shannon-McMillan-Breiman, you can also go and compute the box dimension of the measure, which box dimension is simpler than Hauser dimension in the sense that it's more natural. So it's how many guys you need to cover. It's just a counting guy to whatever power. And this is really like entropy now. Okay, and now if you do it for the measure, then you have to cover sets of positive measure, and then you certainly concentrate on the simplest part to cover because you're taking infimums. So the larger the power r to the d will be the better. But again, since the dimension there delta mu will coincide, in this case you can also show essentially the same. Delta mu is doing the job, so it's also the box dimension. For this times 2 example, or for this one-dimensional expanding maps, you essentially can show most of this. When it comes to other systems, things becomes uglier and more difficult. Actually, one next big problem is when we go and we don't have conformality. So imagine just as simple as in the torus T2, you take this expanding mode. It's times 2 in one direction, times 3 in the other direction. So it's a multiple of times 2 and times 3. Then you just do the same analysis. Now the point is that when you look at the atom of the Markov partition, it will be a rectangle of this size. 3 to the minus n in the vertical direction, 2 to the minus n in the horizontal direction. So it's not anymore a ball. And so if you try to write down dimension asks you to care about balls, not about this very distorted rectangle. So, and if you look to box dimension, it's the same. If you think of outdoor dimension, then it's still essentially the same, even though it gives you more flexibility to discuss things. It's still pretty much the same, especially when you try to follow these formulas that we are doing here. Since now entropy will give me 1 over n mu of these rectangles. Or n. And as I said, this is not really a ball, but now is where really this notion of conditioning here or conditioning there comes into play. So I can take this foliation by verticals, and I can write this measure mu of Rn as integral of the vertical measures of this ball of radius 1 over 3 to the nth y d mu, and now is transversal measure. Through the point x. So this is Huyi Hu Rokhlin on this very small guy, and that's what we get. Now you take log here, and you take log here, and then, as always, first problem arises, which is Jensen inequality. So if you want to send the log inside, you have to pay something. So on one direction it gets trivial, but then the other inequality you still have to fight. So that's first fight to happen, which still people do it, and people are Ledrappier-Young, and tells you that you actually can get inside without killing everyone. And this is very subtle, and this has to do of this function here being actually very close to constant. So you prove at the same time that this limit exists, put the 1 over n here, so that this limit actually exists, and the fact that this limit exists is not trivial and is pretty much the same idea as here. Okay, so you will get log 3 and the dimension of the vertical measures, vertical condition. Now the problem is that if you remember how we prove this here, we rely on a Shannon-McMillan-Breiman theorem to make sure the limit exists. After we knew the limit exists, then the computation of the limit was just whatever you get. Now here is a little bit harder because you don't have the Shannon-McMillan-Breiman, so you have to prove a conditional Shannon-McMillan-Breiman type of theorem. So that's what they do, and actually then they know that this limit exists and is this log 3 times dimension of this vertical direction. And since you know that this is going to a constant, then Jensen is very benign when you are becoming the constant function. And so the log actually can get inside, essentially. Again, all this is pages and pages. And you bring the log inside, and then comes the next subtle thing, which here we are integrating on a ball of radius 1/2 to the n. So actually, I was too fast to send the guy inside. Forget about the 1/n. So, because Jensen is for probability spaces, so if you are going to send inside, you really have to take into account that this is not a probability space, because all this is part of a large guy where you do all this conditioning, okay? But we could do the normalization, but anyway, it's better not to do. So here you multiply and divide one of the measure, mu, transverse measure, and you multiply by this guy. And you get the logarithm. Then, as always, you remove this guy, put the 1 log mu of this dx 1/2 to the n. And now this is a probability when you put this guy with this guy. So Jensen now can be used and sent inside. Assuming we know this fact, this almost everywhere conversion is there. We have 1/n here, 1/n here. This guy is giving me this delta vertical times log 3. This guy, we face the same problem as before, okay? If we knew it was convergent, certainly it's going to log 2 times dimension of this transversal measure. Because this is definition of dimension and this 2 to the n fact. Now, why this limit exists? Well, because this exists, and as we saw, this exists, we imply that this exists, and hence that one exists. And that's the formula. So that's pretty much the proof of Ledrappier-Young in completely simple situation, waving the hands a lot, and bypassing all the true difficulties, but that's pretty much how it goes. Now you see that actually here there is not much of a problem. I could reverse the roles of times 2 and times 3 in this picture. It's not really much of a problem in here. And I will have same formula, so the entropy mu is log 3 times the delta vertical conditional plus log 2 the delta horizontal transversal. So that's what we got here. And we could reverse the roles, even though this looks very thin here and very steep there. There is no harm in swapping the roles, and I could have delta vertical transversal plus log 2 delta horizontal conditional. What I cannot do is make both conditionals or both transversal. So one has to be conditional, the other has to be transversal. It's just what you get from the proof. So it's how you write down this.
Well, you again assume mu is invariant ergodic.
Mu, yeah, here we are assuming mu is invariant ergodic.
They will depend on both.
Yeah, I fully agree. Because this comes from this limiting here. So Shannon-McMillan-Breiman is depending on the point if I don't assume ergodicity, yes. Now, why I can reverse the roles here? Because when I write this guy here, I'm using something which is trivially true here, but one have to be very careful in the general situation, which is I'm taking a transversal, and I'm looking at the distance, this transversal, and this is well defined because this is the foliation by verticals, which is better than Lipschitz, it's just verticals, okay? And the same thing, I have the foliation by horizontals, it's just by horizontal. But if I, instead of having this nice guy by verticals, I had the foliation almost vertical, but which is only Hölder continuous, then I have too much distortion. And then I cannot do anything. And this would happen if I take a perturbation of this guy, for instance. So you take a slight perturbation of this guy, well, there is a lot of problems of no uniqueness for the past and blah, blah, blah. But even if you bypass this problem, you face the problem that this foliation associated to times 3 will be Lipschitz. The foliation that will exist associated with times 2 will not be Lipschitz, will be only Hölder. And then you cannot do the reversed game. But for times 2 times 3, there is no problem. You have both equality. We'll give you some formula which, in principle, I'm not sure is very useful so far, which is that this guy is the same as this. So then you will love to be able to deduce from there that this number is the same as this number and this number is the same as this number, but certainly not. So because there is no, I think you can essentially show with some effort some equality like this and some equality like that. So that's more or less reasonable to expect, at least. But since they go in the opposite direction, so you again get nothing. So, well, you get something, but it's not. It's the defect of this minus this times log 3 is the same as the defect of this times minus this times log 2. So what?
Is it the case that in this case, for any pairs of numbers written down, that you would take our delta vertical and delta horizontal, there's a measure for which they all satisfy?
No, not necessarily. Not at all. It may not, I guess. So this is.
There may be further obstructions, let's say.
Yeah. So in the type of examples like one can build examples of Katok style. Actually, this is what Shuba and Wilkinson do, but again, a slightly different phenomena. Actually, this goes also back to Magnier type of ideas, where essentially you can make this guy atomic and not this guy. This guy atomic. Where is the guy? I lost the guy. The conditional of the log 2. Where is the condition? Here. Where? Yes, this guy. This guy atomic. So this guy equals to 0. So that you can produce, and actually in most, so part of the theorem says that in most examples, this guy will be 0. Maybe not in this time 2 times 3, but in whatever other situation.
So the second line corresponds to considering this 2-3 map as an extension of times 3.
Essentially, exactly.
Weakly expanding.
Exactly. You think of this, that's a way of doing it, yes. Which brings us to something I also wanted to talk about and I forgot, so thanks to bring it here. So yes. So this is these factors and extensions. So a factor is, as always, that you have pi, you have your dynamic f, you have your little dynamic f. If you have a measure, then this measurable factor, and you get this factoring guy. So the diagram commute, meaning that the pi does the conjugancy business. And you say that little f is a factor of capital F, and capital F is an extension of little f. And by the standard theory, assuming everything is measurable and beautiful here, Lebesgue spaces, you get that from a measurable point of view, M is like n times, say, the interval, 0, 1, maybe union the naturals, because that's what all Lebesgue spaces are. And you get that capital F of x, y is little f of x and some gx of y. And then all extensions can be essentially written in this form. Now, we have a Abramov-Rokhlin formula which tell us a very important formula, which in a sense looks a little bit as this form that appears here, and is more or less what Alp was saying, which is that the entropy of F for mu is the entropy in the base plus the entropy in the fiber. Now this is, I'd like it to write it in this form. So it's the entropy of F, but given the fiber. And the definition of this object is the same definition we do for the standard entropy. Simply, we subordinate to the fiber and take conditions on the fiber. So here, remember, when you do definition of entropy, you take a finite partition, you do this game, oops, no x here, with respect to the measure mu, and that's how you do the definition of the standard partition. Now, instead of doing this, essentially you take a conditional here on the point x, and that's it. Of course, you need a theorem saying that, arrow should go the other direction. So you need a theorem saying that this limit exists, plus ergodicity, this is independent of the point x, and then you are happy. So that's pretty much how you do it, and the proof, actually the proof of this Abramov-Rokhlin formula is just going through the basic properties of entropy, of conditioning entropy, plus the really hard part is in showing that this limit is actually existing. But as always, the proof of this limit exists is by showing that the limit is the difference between these two quantities. You have lower bound and upper bound, and that's pretty much how you do it. So now, once we have this again in mind, now we can go back to the formula, and this Ledrappier-Young, in this respect, is here is actually a global factor, but in the general situation is you only think locally, and you look at your system as an extension of your local factor. And this is your factor, which is the slower dynamics is always the factor, because this is what allows you to have this nice Lipschitz picture, and these are the fibers. So this quantity is what gives you this, and this quantity is what is giving you that. So in a local version of it. And again, if you want this formula we are looking here, is no different than what we did here. You put Rokhlin, you do this integration, send the logarithm inside, and all the effort is actually making sure you can send the logarithm inside. Okay, and this is pretty much about limiting, showing that this limit exists for almost every x, and is constant.
Sorry, why take the weaker dynamics at the base?
because it's the fast dynamics which is produce ellipsis foliation. The weak dynamics in general don't produce ellipsis foliation. That's a problem, a geometric problem. Okay, so it's not that you have to always. But in this Ledrappier-Young, when you want to really extract geometry, that's how it goes. It's not that you always do that. Actually, typically in this partially hyperbolic type of world, the typical example will be an Anosov, and then you do, say, a rotation, where this is isometric, so this is low, and you think this as a factor, and this as the fiber, and you take perturbation of this, then even slight perturbation of this typically will be slow, and this will be the fast, and this is the factor, this is the extension. And yeah, you can do it, and even if this is like that, then the center foliation is Lipschitz, so you can even go and find reasonably nice formulas, because this is still Lipschitz foliation. But once you make a perturbation, these foliations stop being Lipschitz. And then even though you can still do things, you will not get these nice geometric dimensional formulas, because dimension is about geometry, and geometry you cannot go beyond Lipschitz because Hölder is already distorting geometry, unless you go to some very coarse games, which is hard to do. I don't know how.
So you're putting the slow dynamics at the base.
You always put the slow dynamics in the base.
Slow or strong?
Slow. In Ledrappier-Young, you put the slow dynamics in the base.
But
here you put the fast. But this is not the Ledrappier-Young picture. So this writing is not coherent, so to speak, with Ledrappier. So actually, maybe let me rephrase it, because I'm putting two theorems together and just getting the outcome. And actually, what you do is you put in the fiber the Lipschitz guys, the fibers that form a Lipschitz foliation. That's what you put in the fiber. If you have it is low, it is fast, doesn't matter. If it is forming a Lipschitz foliation, you are allowed to put it as fiber. That's theorem 1. Theorem 2 is if it is the fast dynamics, this foliation is Lipschitz. So you are allowed to put them as fiber. There may be other reasons, like in this very specific example, where the slow dynamics is forming a Lipschitz foliation, and then you are happy. Okay? Again, this is a very subtle business where you are playing together geometry and dynamics, and this is very special of smooth dynamics. So if you go to abstract ergodic theory, then there is no smoothness, so the notion of Lipschitzness disappears, because once you start putting Lipschitzness, you start talking about smooth dynamics. Okay? So Abramov-Rokhlin is a purely ergodic theoretic statement. So there is no smoothness, no nothing here. So it's about entropies. Entropy here is entropy here plus entropy there. Okay? Now, all this discussion about Lipschitz or not Lipschitz is when you try to transform these entropy quantities, these information theory quantities, into geometric quantities, which is dimensions and expansion coefficients. Then when you want to transform this into dimension and expansion coefficient, you need this quotient space to have some nice smooth structure. A nice smooth structure means, in particular, that this pi is a smooth function, or at least Lipschitz. So because I could make n into very nice smooth space and even the f to be a real analytic guy, but if the pi is not smooth, this is useless when I try to play geometry versus ergodic theory. And so that is what is done up there, and that's what I'm saying about putting in the fiber the fast is what guarantees you that this pi will be Lipschitz. And then you really split the total dimension of the guy into dimension here and dimension here. Yeah, I forgot to say one more thing here, which is very important. Which again follows from the existence of all the limits plus Jensen plan blah blah blah. So it's really doing pretty much similar computations, although it really requires a proof. The fact that the dimension of mu exists and is equal this sum. It's a second formula. Okay, which is now is pretty much the same game. Instead of taking the measure of this thin rectangle, you go to this large rectangle, which is 2 to the minus n here and 2 to the minus n here, and go and measure this guy. Yeah. And then you show that you do a pretty much similar computation there. But that time you know that these limits exist already, so you have really room to play. So you first prove the entropy and then go and check the dimension business. Okay. So this was, I guess, a 2-day crash course on Ledrappier-Young theory. And I insist, when you have the, so this is hard, not easy, but what is really harder is the previous theorem we stated in last Monday, which is the fact that the entropy of the system comes from the entropy appearing in the unstable. And this is especially hard when you have zero exponents. That's really hard. This is not that it's really simple. It's more or less the same level of difficulty than the other, but it's not more difficult than dealing with zero exponents. Okay, so once we have this, now I will try to state a setting where we can really do something. And do something means that I want now to split and to have that these are both conditional quantities. Okay, not transverse, but both conditional. I really want to put myself in a setting where this would be true. And it's almost never true unless something really amazing happens. And it certainly is true if you have that, if I knew, so my system, I wrote it as a matrix, but now I really want to write it as times 2 times 3, then I take the measuring variant by times 2 times the measuring variant times 3, and I call it mu. And then here everything is nice, because the entropy of mu will be the entropy for T2 times 2 plus and then for this measure, I know that is the dimension of nu2, which is the conditional measure, and here is dimension of nu3, which is the conditional measures, and life is nice. So I could define in general for any measure also, which we already defined essentially, h mu of t given the psi2 guy, and also I could define this, where this here corresponding to this ordering log 2, log 3. So this is supposed to be what we used to call V1, and these two guys together is V2. But here, for some reason, which is not coming from Pesin theory, it's coming from how I know things, I have also a foliation associated to this log 2 direction. So I do have it, and since I do have it, I can consider this guy as well. So if I apply the same proof as before and the Ledrappier-Young, blah, 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 I get that this is log 3 times the conditional along the log 3 direction. And this is log 2 times the conditional along the log 2 direction. Okay, so that's okay. Now, for a general measure mu, is it true that the sum of this plus this gives me entropy of this entropy contribution and this entropy contribution is? And the answer, as I already remarked, and I will keep on remarking, is no, because this equality will amount to have the transverse measure to be the same as the conditional measure. Okay, so unless I know that, it's almost hopeless. And even though it's not an implication, is a lot of evidence, and is almost an implication, the fact that if I had the equality, then I am having a product of measures. So actually problem, if you want to play a little bit, is show that if h mu f t, actually because it's this t, is equals to h mu t psi 2 plus I'm sorry, show an example of mu ergodic, this and mu is not a product measure. Okay, so this means that the equality here is very close to imply the measure is a product, but it's not really the same. Okay, and then if you want the hard problem, is find an example with h mu t positive. Okay, so that will be a little bit harder. And the third problem would be to find the correct statement that will imply that the measure is a product measure. So what's the correct equivalence between entropy here and entropy there that will make the measure actually the product measure? Now, in any event, even if you don't have the product structure for the measures, it's good to have the product structure for the entropies. So this is a very useful quantity, even if you don't have the product structure for the measures. And that should be the theorem, but I promise not to go over time, and it's 3:20. So on Friday, I will now go to these higher rank actions, CK acting, and I will show how much one can show in this CK setting. Okay, thanks. Okay, so yeah, I want to add one more statement by Ledrappier and Young, which is very important for the theory, which says the following. let f from n to m C1 plus algebra diffio mu an invariant ergodic measure then h mu f is the integral of log of the unstable Jacobian of f d mu, and this is Pesin entropy formula. If and only if the conditional measures along the unstable manifolds is absolutely continuous with respect to Lebesgue on the unstable manifold, and in this case this Radon-Nikodym derivative is given by the formula product k larger than 0 Jacobian unstable Jacobian of f on f k negative of y. I think that way it could be 1 over that. It's either that or the inverse of that. It's not so important. So it's important that you have a very precise formula. Let me see if I iterate this guy. Here I get this, and here I get that. Yeah, I think that's the correct formula. I may be wrong. You check it. So the Pesin entropy formula holds if and only if the conditional measure is Lebesgue along unstables. Okay, so one implication was essentially Pesin's works, even though Pesin do it for when the measure mu is Lebesgue measure, but the same proof by Pesin holds in this if you assume that the unstable conditionals are absolutely continuous. And what Ledrappier-Young shows is the other implication, that if you have equality, then you have this property here. The proof is actually not too hard once you have the previous theorem, knowing that this entropy contribution here is the entropy along the unstables. And then you just do some Jensen inequality in some game, and you get it. So I will not get into it. There is some subtleties, some non-trivial subtleties, which are very important and useful in the proof, which has to do with the fact that this quantity here, which actually belongs, so this is C, same amount of differentiability essentially along on the y variable. So it's as smooth as the dynamics essentially. So in particular, it's positive everywhere. It's not vanishing, bounded above and, well, bounded from infinity, so it's a finite number and positive number everywhere, which means that these two measures are equivalent. So, which is not completely obvious to begin with. So why the fact that the measure is absolutely continuous implies that it's equivalent and even is given by this formula. But that's the case. And actually, this theorem solves one thing that we were discussing some time ago. So let me show you what's the solution. So let's go back. Actually, it's not exactly this statement, but a similar statement that one could prove in the setting I'm going to write down now. So remember that case where I have this let's say I have one S direction here in the ij direction. This was and we have our dynamics a to the t, e to the t1, e to the tn, and we have an invariant measure mu. We consider the mu ij. We look at the group, which are all the translations from R to R, such that translations T star mu ij x is equivalent to this, and here as always we do this identification of the reals with this group here. And then we have this group, and there was one case where this group is the same as R, and then in this case we get that this mu xij is e to the beta, or dt is, this is e to the beta t dt. Okay, we just go to do the computation, and you have a measure which is invariant by translations up to a number. It has to be of this form. But then we want beta to be 0. Okay? And you can do it in several ways, and here is one of the ways you can do it, because when you look at this Radon-Nikodym derivative, it has to be this product. But now in this situation, this product is a constant number, because what you have up here is the same as what you have down there. So it's 1. So you get a 1 here. That's it. Okay, so that's a very nice application of this. I will show later maybe other applications and other related results associated to this formula. But before that, we go back to our actions, to this type of settings, and we see how this Ledrappier-Young theory fits into these higher rank actions, because this is very useful to try to understand this global picture of what's going on. So first, what does Oseledet's theorem say? Oseledet's theorem. So now we have an action alpha ck or rk. I like the integers, but rk will not make any difference. Say C1 plus Helder. You don't need C1 plus Helder to apply Oseredet, just C1 will do. And actually, it's very explicit. It's about cocycles, Oseledet's theorem. So you just need measurable cocycle with some integrability property. What type of integrability is a little bit subtle. I will not enter into this discussion. So, but you need essentially a little bit than log L1. So mu an ergodic invariant measure. You don't need ergodic, but you can always assume it's ergodic. So I like to work with ergodic. Ergodic for the whole action. And you need, well, that would be the standard type of assumption. this, and for the co-norm as well. Well, if it is for every n, then that's good enough. One could put a plus here just to care about the positive part, and then the n will do the job. So this for every n. So if it were just a C action, then this would be enough. Okay? Now this, since we are really caring about the CK actions, this is not good enough. And what you need essentially is that this quantity, so these functions, belong, so for every n, how will you do it? Yeah, this belongs to L K, and I think it's LK1. And these some Lorentzian LK spaces you can go and Google. So it's some result from the 90s. I forgot the authors, which they don't do it, I think, I'm not sure they do Oscillades. No, I think they even go and do Oscillades or the multiplicative ergodic theorem, but naturally you get from what they are doing Oscillades. Probably they are even doing Oscillades. But yeah, so you need this a little bit better than L1. Well, actually, quite much better, but still. L infinity will certainly do it. So that's how it is. So you need it just, if you really care and need it, so we can, I can give you whatever reference needed. But what I want you to just make sure you remember is that you need a little bit better than L1, and then you will know where to search what is the right thing. And you can build examples of cocycles where you don't have a nice Oscillades theorem if you don't put something like that. You will have some Oscillades theorem, and the problem is that you will want to apply everything that will be discussed now, something good that I will explain what is the good thing you want. Okay, so we have this, we have the ergodic measure, and now it comes to Oscillades. So Oscillades, what tells you? It tells you that Tm splits as E1 x plus EL of x. And it gives us, and remember, we already went a little bit through it when it was matrices. Now it's just the dynamics. We have psi I, which are not numbers, like the standard Oscillades. It's functionals, because it depends on the element of the action we are taking. So naturally, this functional tends to Rk. That's why I'm directly writing it as being from Rk into R, such that for every such that the following, and here is what comes slightly different from the standard Oscillades writing. It's let me write it correctly. I want okay, norm of d alpha n applied to a vector vi over the point x. Now I take the logarithm of this. I remove chi I of n, which is the amount it's supposed to grow. I divide it by the norm of n, and this goes to 0 as modulus of n goes to 8 for every bi in ei of x minus 0. Okay, so that's exactly what this Oscillades tells you. So the standard Oscillades will tell you something a little bit different. Let me just write it down here. What will standard oscillator tell you? It will tell you that 1 over k log k times n bi, this goes to chi I of n. Okay, so this is true for every n, and for almost every x as well, and same bi's and blah blah. So when you go to the picture, so if this is r squared or c squared for that matter, so this is telling you that when you go to infinity along this ray, then you have the right thing. But having the right bound or the right limit when you go along rays doesn't imply that you have the right estimate when you grow whichever y you want to infinity. And this is what you really care. And so for this property, you just care about L1. So you don't need more than L1 for this. And there is a lot of things you can just do with this property. But if you want better than this L1, than these previous things, and you want something like this, that's the reason you want a little bit more on the cocycle. Okay, other than that, it's actually, this is needed for standard cocycles. So if you want, so these are multiplicative cocycles. If you want, or submultiplicative cocycles, if you want to do for standard real valued cocycles, you want to have some control of this sort, you still need something like that. Okay, so if not, you only have one dimension conversion. Anyway, okay, so that's essentially what it tells you, and of course it tells you, as always, the angle between the alpha n of ei, or actually ei alpha n of x and ej alpha n of x, this log of this 1 over n, this goes to 0 as n goes to infinity. So I different from j, because if I equals to j, then this is minus infinity or whatever, so I don't know how to define log of 0, so I don't do it. So this is telling us that this angle is not getting exponentially small. Okay, in the nice situation, it will be bounded away from 0, but that's Pesin theory. So even if this angle gets small, it doesn't get exponentially small. Okay, so that's oscillated. Now, here is a very important picture coming from oscillates that we have seen it already in the case of matrix, essentially. But now we are in the general situation, which are, we have the kernels of chi I. So you have L of this guy, you have L kernels. But some of these kernels could coincide, because you may have chi1 equals to minus chi2, and then the kernel will coincide. The way oscillator tells you is give you that if chi1 equals to chi2, then the vector e1 and e2 are added up and they form the same thing. So this you will never have, essentially. Even if you have it, you are putting these guys together. Eventually, at a later level, you may want to separate them, but this will not happen. But this could happen, and this will be naturally separated. And you don't want to put them together, or maybe you want, and that's what we are going to do now. So.
And you assume that all exponents are non-zero?
No, there may be zeros there. Yeah, there is one kernel that may be everything. But it's just one. Because one zero exponent is just one zero exponent. Sorry, not one dimensional, but it's one zero exponent. So the ER corresponding to the zero exponent is one of the guys. All the rest correspond to non-zero. And here there is no ordering of who is smaller and who is larger because it's functional. So there are no smaller or larger. You just pick some ordering coming from whatever. So we say chi1 is positively proportional with chi2 if there is C positive such that chi1 is C times chi2. Okay? So they are proportional by a positive. And if C is negative, you can call them negatively proportional, of course. This is relevant, but not is not what I want to do now. So I want to talk about coarse direction. So we define E chi as being the sum of all the EI such that chi I is Ci for some Ci positive. So I'm adding all directions which are positively proportional. And then I have a new splitting which is E1 ER of coarse directions. Now this coarse direction has a characterization which is extremely important and is the following, which is about whether you can separate or not separate the elements. But for this, let me make one definition. Define, oops, not W, but E. EU of n, for n in Ck, is the sum of all the EIs where chi I of n is positive. Okay, and naturally ESN is same thing, chi IN negative, and ECN is chi IN 0 of EI. And these guys in principle depend on the value of n, but you see that they only depends on this being positive is locally constant. So if you move a little bit, this guy will not stop being negative or positive. And essentially, typically you will have the same guy. When I say moving only a little bit, it's better if you think of RK, even though it can make sense. You go close to infinity or think projectively. And what I'm saying is correct projectively in CK. And now it's not discrete projectively. Of course, this is very unstable in principle. Unless the exponent is fully 0, you move a little bit, and you typically should send this guy either here or there. But anyway, the whole point of this quartz guy is that V and W, okay, two non-zero vectors V and W belong to different coarse directions. And let me remind you, coarse directions are these guys. so coarse Lyapunov directions. If and only if there exists n in Ck and chi I chi j such that chi I of n is negative, chi j of n is positive, B belongs to EI, W belongs to EJ. Okay, so in order not to belong to the very same quartz direction, I need to belong to two different Lyapunov directions, EI, IJ, which are not positively proportional. Okay, it's directly from the definition, but that's important because it means, thanks to this definition, i.e., there exists n such that V belongs to the ES n and W belongs to the EU n. Okay, and actually, well, there is always the problem with the zero direction. Let's assume, so the zero direction is an extra guy. Let's say B in W, not in the E naught. Because the zero, the Lyapunov exponent is a very special guy.
So here, do you care if I and j are different, or maybe the same?
Well, they cannot be different because by the same value of n, one have to be positive and the other negative. But then I can forget about the I and j's, and that's why I'm doing this definition. You see? So that if I can make one contracting at the same time that the other is expanding, then they don't belong to the same quartz. Otherwise, they have to belong, whenever one is in the stable, the other has to be in the stable. Whenever one is in the unstable, the other has to be in the stable. So the quartz directions are the vectors that I cannot separate. And what does it mean separating? Means when I make one contracting, I make the other expanding. So that means separation. And that's a consequence of this observation plus this definition give me a second possible definition of this quartz direction, which is very important. So all I'm discussing now is just purely linear algebra. Okay, so about a bunch of functionals and how these EIs are defined.
And these components are measurable, right?
All these bundles are measurable, yes. And some of measurable bundles will be measurable, so then the E chi are measurable. Yeah, I didn't say they are constant dimensional and measurable. So, lemma E chi is the same as the intersection of the EU, so for chi different from 0. So this is a functional, I'm talking about the non-zero functional. So of all the EU n such that chi of n is positive. Okay, and this is trivially the same as the intersection of chi of n negative of ESn, and that's simply because ES of minus n is EU of n. So that gives you equality between these two quantities. This is the guy. So, so the quartz direction is a direction where all the guys contract or expand at the same time. And then, of course, E0 is intersection of EC and if you cannot make a vector contracting or expanding ever, no matter the n you are choosing, it's because the guy belongs to E naught.
So for the definition of what is it? It's the zero course bundle. So do you have one Lyapunov exponent that is zero, or can you have more than one?
Well, by definition, it's only one because we admit multiplicities. But it's only one with multiplicity, which is the dimension of E naught. So by definition, E naught is equal to E naught, even though in the numbering there. So if you want, let me write it that way. So, and they have whatever multiplicity they need to have. So I like in general to take, so given a coarse Lyapunov direction, E chi, so this chi is not uniquely determined because any positively proportional will do the same job. So I like to choose a very specific one of all the possible proportional functionals. So we take chi equal to sum of dimension of EI times the chi I, where chi I is positively proportional to chi. Okay, and since all the chi i's are positively proportional, this is essentially, so chi is the log of the Jacobian of alpha, so chi of n. Actually, this is even true if I write it. I don't need this, so chi of n is the integral of log of the Jacobian of alpha n restricted to the chi direction. D. Okay. So defining it this way or defining it this way is exactly the same thing. And so this in this way is a little bit more canonical who is the chi when you look at talk about coarse Lyapunov. And I find it useful for the formulas to make this choice of chi. But again, any other choice of chi will just prompt a positive number out from it. Okay. There could be other choices which are as well reasonable, other typical choices taking the chi I with largest positive proportion. So it means that any other chi j will be a multiple less than 1 from this chi. So it's taking the largest weight. Okay. So this is coarse Lyapunov exponents. Now let's forget them for a second. I want to write down a theorem which is very important in this Ledrappier-Young theory, but for high rank actions. And it's really the basis that permits you to do a lot of computations and games. So, yeah, let's erase here. I will state it slightly different from what was stated originally by its author, which is Huyi Hu. So the theorem says as follows. So let alpha M is always compact connected, so we don't care about the log integrability. It's always automatic here. Mu an ergodic invariant measure. And then take n and m such that EUN is equal to EUM. Okay, so two elements which has the very same unstable. So the guys could be one a power of the other, could be the same guy, could be very close projectively, so that these are the same. Then there exists psi u, a Sinai partition. So remember, Sinai partition is inside of the unstable foliation. So psi ux is contained in Wn of x. Here I have to emphasize who is the element that I'm taking when I'm considering Wu, which is n and m, which will be the same because it's the same manifold. It contains a neighborhood of x, is bounded there. And here, what is really important, remember what was really important about Sinai partition was the bullet that I forgot, which I put it later, which is that this partition is increasing. So when I do alpha n of psi u of x, it contains the psi u. Okay, and Sinai would do it for one guy, and Huyi Hu does it for both guys at the same time. And this is extremely important, that I can pick both at the same time. The proof is tricky, yet you essentially do the same thing that Sinai did. So you add whenever you don't get the Markov property, so the increasing property, you enlarge a little bit your guy. Okay? The problem is, and why it is tricky is because you don't want to enlarge too much. You want to make sure at some point you stop enlarging, or rather than stopping, you want some convergent series. And here you're enlarging because you iterate by n, you're enlarging because you iterated by m. And then you are starting doing all possible combinations of n and m's. So if this is the n direction, this is the m direction, actually you are doing k times here, then sometimes n here, so you have the whole cone. And this very property is telling you that the partition works for all the guys in the cone. And knowing that, you prepare yourself to make it invariant by the whole cone. And you enlarge so that it fits the whole cone. And well, you work a little bit, as I said, and you finally get it. But this is very, very important, because as a corollary of this,
And Sinai partition to be sort of increasing with respect to any number of guys as long as their unstables are the same.
yes, but you have to be slightly careful, as you said. So here is the limiting problem that, so let's say this is, let's say it's a C-square action, just to make our life easy. You have kernel of chi1, kernel of chi2, and these are just boundary of what we call the Veil chamber. So all inside here, they have the very same unstable. Now, as you said, if I take whatever finite amount of guys, actually 2 is good enough for this picture, because I take the outermost And if it works for this guy and this guy, it will work for whoever in the middle. Then that I can do. But when I take guys which are very, very close to the boundary, then I start having problems a priori. And that's why one has to be careful here. Because when this guy is getting closer and closer to the boundary, this deteriorates. So you still can build it, but you cannot build that one that will work all the way up to the boundary. And that naturally cannot do it, because when you reach the boundary, there is one vector in the unstable that is not anymore expanding. And then since this direction is not anymore expanding, you cannot hope to have this inclusion. So of course you may hope to have some equality along some direction, but this is not robust, having an equality. So that's why this is almost hopeless to have it when you go exactly to the boundary. So that's why whenever you pick a cone inside, you are safe. You cannot get uniform all the way to the boundary. So finitely many guys is good, infinitely many is not good. Okay, so yet the corollary of it, because what is important is the application, and for the application, this problem disappears, which means that if EU of n is the same as U of m, then the entropy for m plus m is the same as the entropy for m plus the entropy for m. So the entropy functional is linear all the way here. And this just follows from Ledrappier-Young entropy formula, not even Ledrappier-Young, well, yeah, you can even get it before Ledrappier-Young. Okay, let me go back and say again what I say. So this follows from the fact that h mu for this guy will be the same as with respect to this partition created by Huyi Hu. And now when you compute with respect to this partition, which is both increasing for alpha n and increasing for alpha m, and also increasing for alpha n plus m by direct computation, this guy is the guy that will split. And then again you apply the Ledrappier-Young and you get that this is this plus, and this equality here just follows the definition of entropy, okay, of a partition, of an increasing partition. Now the good news is that we may not have a partition that works for all the Weil chamber. But if I pick any n and m, no matter how close I am to the boundary, there will be one partition. I prove the equality, and after I prove the equality, the partition disappears. So I still get the formula all the way, which means that on this cone, on each Weil chamber, by definition, Weil chamber is the entropy is linear. So corollary of this, well, maybe let me remind you what is Weil chamber. Weil chamber equal connected component of a complement of union of kernel of chi I. So all non-zero vectors. So I pick all the union of the codimension 1 kernels, take the complement, it's a bunch of cones. Take each connected component will be a cone which is called a Bell chamber. And then the second corollary is H mu restricted, so this is a function from Ck into R naturally. So is linear on the complement on each Bell chamber. And even one can go and think a little bit further, but I will not do it right now. Now I want to finish in these last 2 minutes to show you how much more this is telling you as what you are supposed to know for free. Okay, and for this I want to show you an example. So let's say you have 3 guys. Just 3 of them, like A and B in T3 commuting. Because this applies even in this situation. For the 2 matrices commuting in T3, you need this theorem to do the things. So here we have these 3 directions. K1, K2, K3, say. So remember the sum of the 3 is zeros. So here is K1 positive and negative. Then I do K2 positive and negative. And then K3 has to be negative here, positive here. And let's see if I get it correct here. Plus, plus, minus. Then we swap to minus, plus, minus. And then we sub to minus, plus, plus. And now we are good. Minus, minus, plus. And plus, minus, plus. And plus, minus, minus. Okay. So now we say I land here, pick whatever guys n and m there. And here actually I will have one important line that I'm drawing here, which is where K1 equals to K2. So since I guess I should be able to do it, so okay, let's say up here K1 is larger than K2. I hope I'm doing it correctly. Down here is K2 is smaller than K1. I think it's correct. No, that sounds reasonable. Okay. So when I am on all this region, so I take K1 larger than K2, positive larger than K3, then Ledrappier-Young tells me that on this region, this is K1 delta 1 conditional plus K2 delta 2 transverse plus K3 delta 3, and delta 3 is just one dimensional, so we don't care. And I should have evaluated in the place. Okay, and so naturally this is linear because these dimensions delta 1 conditional, delta 2 transversal, and delta 3, in principle they may depend on n, and they actually depend on n, but it's locally constant because these are conditional measures along the E1 direction, and this is independent of the dynamics. What is this conditional measure? So it only depends on what is this foliation. What is the transverse guy? Well, here depends on who you are calling transverse and who you are calling conditional. But that's how much it is. Now, on the second region, chi1, chi2 larger than chi1, positive larger than chi3, we get that similar formula, but now is this guy comes with a transversal, this guy comes with a conditional, and the chi3, of course, is a nice guy. And I only, oh, sorry, I should only add the positive guys. So, okay, let's forget about it. Now we are good. I shouldn't add the negative exponents to the entropy formula. Okay. Now this guy now is linear down here. So this you got for free. Now what Huyi Hu is telling us is that this functional, this h mu, is linear in the whole region, regardless of who is the yellow guy. And this automatically implies that this number is equal to this number, and this number is equal to this number. Because it's just a very easy linear algebra. Again, if you have you have two linear maps. Here you have one linear map, a second linear map. Okay? And if they agree on a cone, then actually they only need to agree on an open set or two linearly independent vectors, because you're in dimension 2 here, then the coefficient has to fully agree. So that's it. So this tells you that this, which as we know from the examples, the Shub-Wilkinson type examples, and all the discussion we have had, so this in general wouldn't happen. So in the standard Shub-Wilkinson type of example, this will be 0, this will be 1. Okay? And here the conditional, the transverse are the same. So of course here you didn't need Huyi Hu in this very specific example, because the mistake I made of putting the chi3 direction would have solved you the issue here, because you could have used the fact that h mu alpha n is also minus delta 3 chi3 of n, and this is certainly fully linear on the open set. So then I could have used this formula instead of Huyi Hu. But when you want to do it in full generality, and you have much more exponent, then this other guy also will be switching sides, and you may have negatively proportional or things of this sort, and then you really need Huyi Hu if you want to do all situations. So if you want to do some situation, you can even go and do it without Huyi Hu.
So what is the significance of these chi-i's being locally constant? Like,
the delta i's being locally constant?
No, the chi-i's.
No, the chi-i's are not locally constant, so they are functions.
Yes,
so
delta i's being yes.
So, so this is the fact that the entropy has two contributions. One is geometry, which is given by the delta i's, and the other is expansion, which is where the dynamics take into place. And the geometry is the same no matter who is the alpha n you are picking. And this is where commutativity is so important. And that's the main source of rigidity in these commuting guys, come from these delta i's being locally constant. Because it's telling you that when you have two commuting systems, the underlying geometry is shared, is the same. And even though they go at different speeds, the underlying geometry is the same. And that's exactly what is reflected here. So the speeds are different when you move the n, but the geometry is the same. And here is, so the fact that Huyi Hu proved his theorem is the very source of rigidity. Of course, one would expect it because one expects this geometry to be shared, but one have to prove it as always. So, and this is the fact that you can go through here without changing the dice even. So this is more than locally constant. It's constant as long as nothing changes. So, okay. So what I will do on Monday is actually write down the ultimate entropy formula for these high rank actions, which is pretty much a corollary of what we wrote plus a lot of linear algebra and not much more. So of course you have to do Huyi Hu relative to something, but it's essentially all the main ingredients are already in the blackboard, and then you get the ultimate formula. Okay, that's it for today. See you on Monday.